So if there's, say, 100 watts per square meter, and you've got the first polarizer, right? Maybe that's vertically polarizing, right? So this is unpolarized, right? Right? Now suddenly you've got light that is vertically polarized, right? So you have 50 watts per square meter vertically polarized, right? Assuming that it's 100%, you know, the filter is 100%, right? Okay. Then you've got another filter, and this one has been tilted so that it's askew. See if I can draw that, right? Okay. So this one's been tilted through some angle, right? Okay, and then what comes out of here is going to be 50 watts per square meter times the cosine of the angle between them, right? So maybe it's 20 degrees, right? Right, that's assuming that this angle here is 20 degrees, right? And then you got to square that.
Don't do it. Do it.
Do it.
No. Jump. Don't know where the person you are. The bad one. Yeah. No. You tell him.
So two polarizers are at a 37-degree angle with each other. There's 235 watts per square meter of light incident on the first filter. So this is like this, right? Here these guys are. Right now these guys are 0 degrees with each other, right? And then 37 is like, we have a possible 37-degree angle, something like that, right? Okay. Like that. That's what we're talking about. Okay. So let's solve this problem. So we have 235 watts. When it hits the first filter, we cut it down by half, because if you take a random, assuming the light is just totally random and unpolarized, right? Half of it will be on the average vertically, right? So 235 divided by 2. So you get 117.5 between the filters, right? Watts per square meter. And now we're all set. Now we can use that 37-degree angle. And then after this, it's 117.5. So here's our tilted one. Right now it's 117.5 cos 37, cos squared 37, right? So that, let me check my mode here. I am in degrees. Okay, so that 117.5 cos 37 squared 74.9. Yeah, if it's a dual filter light and they tell you unpolarized light, then the first filter cuts it in half. If it's an ideal filter, and if it's not, I don't know what you do, right? Okay, so if it's an ideal filter, it cuts it in half, because on the average, half the light's going to be horizontal and half vertical, right? Okay, because really, light that is at some angle, if light comes through, let's say we've got a horizontal filter, and light comes through at this angle, it's not that the light, like none of that light gets through, it's that this component of the light gets through, this component is entirely blocked, yes? Right? That's what really happens, is it only blocks the horizontal component, it allows the vertical through. Same with a spring. If I'm trying to wiggle it at some angle, right, it's going to let, if it's a vertical thing, it'll let it move vertically but not horizontally. How do you what? Oh, how physically? This is a good question, and I can answer this, I think. Okay, those filters, what they have are long chains of molecules that short circuit the electric field if it's perpendicular to them, but allow it through if it's parallel or something like that. Yeah, or maybe it's the other way, I don't know, but it actually has to do with the molecules themselves, which is why filters like that are actually somewhat spendy. Yeah. 117.5? That's this guy divided by 2, right? Because when it goes through the first filter, it loses half its brightness, right? Yeah. Now, if they give you a problem where they say you have 500 watts per square meter of vertically polarized light, well, then it's already polarized, right? And then it hits a filter that's 37 degrees with the vertical, well then you're set, just use the 500, right? So this thing, basically this guy here has to be light, polarized light. Right, this guy has to be polarized light, and this is the angle the filter makes with that, right? Yeah, so it has to be. All right. A little applause. Are we good? How good are we? Her favorite subject was thermodynamics, not so much waves, apparently. She's drawn some good pictures, though. Yeah, her pictures look really nice. Looks like she studied. All right. Yay. Go team. Now, the next concept is that when light bounces off reflective surfaces, like water, this is a good example. Water is a good example. Water is a good example. Glass. That light tends to be polarized well parallel to that surface because the component of the light that is perpendicular, where the electric field is perpendicular, tends to get absorbed, and the component that is parallel, so if it's like this, if it's like that, that tends to get absorbed by the surface. But this stuff, if it's polarized like that, this stuff, so useful, and this stuff tends to reflect. So when it bounces off a horizontal surface, it tends to be polarized horizontally. If it bounces off a vertical surface, it tends to be polarized. If it bounces off the wall like this, it'll be polarized vertically. Yes? Now, how many photographers do we have here? How many people have used? Nobody has. Has anybody used a polarized filter on their camera? Yeah, any reflective surface like clouds, where you're seeing you're seeing light that's bounced off of water, correct? Grass is actually shiny. Okay, you're seeing light that's reflecting off that, or water like that. You can use a polarized filter and you can mess with it, right? So first thing I'm going to do is I'm going to pass around some polarized filters. And if somebody hands me a filter and I want to know which way it's polarized, it's very simple to determine this. All I do is I take myself and I find some glare. So right now I'm seeing the glare of that light up there in the desk. I know that the light that's coming off of there is mostly polarized this way. So if I take this thing and I rotate it, okay, like that, now I see the glare, now I don't. Now I see it, now I don't. If I don't see it, then let's see, it must be, I guess, polarized vertically. Yeah? Jim Shen. All right. Time for a change. Pass that back. Okay, so basically, when I've got the filter in the direction of it, I can see it. When I don't, right? So I'm looking at the glare. So when I'm passing these around, that's the thing to do, is you need to see the reflection in one of these desktops of a distant light, right? And right now I can see it, so it must be polarized this way. So it's polarized parallel to the minor axis of this, yeah? And now I cannot see it. See it? Cannot see it. It's very cool. Right? Then you can, of course, look at the room, and really very little else changes. So what if I wanted to reduce the glare? Roadways are just rocks with the surfaces worn shiny by cars. Sun will glare off that, won't it? Doesn't that hurt your eyes? Right? Aren't most surfaces horizontal? Water on the road, like that. Polarize them vertically. Yeah? Yeah? How about, what if we put vertical polarized filters on all headlights and everybody wore horizontal, or I don't know, or vice versa, filters on their sunglasses, right? Windshields, and we wouldn't see the headlights. Of course, that's not good. It's good to see headlights. I don't know, right? So I'll pass these around, and you can try that. Please don't touch the little thing in the middle there. The other thing to do is to, oh, the screen's not doing it. We can also